workshop and accepted by Ayush Jain on energy-based models as usual planners for compositional scene rearrangement. Floor is yours.
Hi everyone, I'm Ayush Jain, and today I'll be presenting our work on energy-based models, zero-shot planners for compositional scene rearrangement. So understanding language has been a long-standing goal in our community, and even back in 1968, we had models like Sherdlow, which would take a language instruction and try to map it into some actionable representations. These models were typically rule-based and were very hard to extend to more general kind of scenarios. But nowadays, for example, we see large models like Clipboard, Parat, and maybe more famously RT1 and RT2 that directly takes the language instruction and map it to the action in the robot interactive space. These models typically take the input image, language instruction, map them to the language, and this works great and has been following the works in NLP literature and computer vision, where you just scale up the data, let the model do everything, and things hopefully work very well. But the main problem here is that this kind of approach mixes the language understanding and execution. So this model also needs to understand what the language means, what the objects are, what these concepts mean, as well as how to actually manipulate these objects. And this requires a lot of kinesthetic data, which we don't really have access to in at least our robotics community. So instead, what we can do is map the language to some sort of sub-goals and then map these sub-goals to actions. And what this allows us to do is learn some things about how the world works from the observation data and how to manipulate the objects and so on from some kinesthetic data. This is very similar to what Animesh was saying, that we should separate what and how while building these manipulation systems. Now, the next question is basically like, what should be the representation of our sub-goals? Well, one very common representation these days is language itself, where works like Inner Monologue, Say, Can, Code as Policies, and FAMI try to map the input image and the language instruction to some simpler language sentence like this complicated, move the blocks into mismatching goals. It does its reasoning and just simply say, oh, you just need to move yellow block to red ball. You don't really need to understand what mismatching goals and so on means for the action policy. It just needs to execute the low-level action. And this is a language as a subgoal is very useful and is very useful for many different tasks. But sometimes language becomes a bottleneck. For example, especially if you want to communicate multiple constraints jointly at the same time, it's very hard to do in the language space. So for example, here we want to put the strawberry to the right of the apple, as well as to be in front of the green bowl simultaneously. And this means that this action policy needs to satisfy both these constraints jointly. And if we just specify one constraint at a time, we might not likely end up at a position which satisfies both the constraints simultaneously. Also, some things are just hard to describe in language. Many fine-grained kind of concepts require you to basically see how the goal actually looks like instead of trying to describe something like this in words. So another common representation in the community is pixel space image subgoals, and popular methods like SUSY, Unisym, and UniPy follow these kinds of approaches, where you take the input image and the language instruction, and you use the large diffusion model or something like that to generate an image goal. And this image goal and the input observation can be used by some inverse dynamics model that actually produces the action. And this is nice because now we can represent very fine-grained concepts very easily in the image goal space, and we don't have the limitations that the language has. But I would argue that this image subgoals is not causal. So even our best video diffusion models like Sora can produce pixels just out of thin air, unlike what actually exists in the real world, where objects move because you interacted with them. And that's why I think it's not causal in nature, and it's very hard for the inverse dynamics models to actually execute things correctly. So in this work, what we propose is we should build subgoals in the object-centric motion graph space. What this basically means is that we won't be reasoning in terms of pixel space, but we would be reasoning how the objects should move so that they move to the right goal location in terms of these bounding box representations. And once we have these goal representation, we would just use a simple action policy or an inverse dynamics model to map it to the actions. Now, to get these object-centric motion graphs, there are many different ways, and we would need some sort of a generative model. And some properties that we would like for this generative model to have is it should be able to represent multimodality in the spatial location space, because you can imagine that multiple spatial locations can satisfy the concept at the same time. And energy-based models is one of those generative models. Very brief description of what energy-based models is. It's basically trying to model the probability distribution of the data. The energy function E basically takes in as an input representation X. This can be an object, this can be an image, this can be a collection of objects, and it tries to score it. So what this means is that if we are talking about a square energy, this configuration would be assigned an energy of 0 if it satisfies the concept of square. If the configuration is slightly off, we would assign it some higher energy. This can be trained in a normal maximum data likelihood way. But the interesting thing is that when we do this training optimization, what it turns out is we are basically taking our true data x plus, and we are trying to push the energy of this data x plus down. And we are generating a new hallucinated example sampled from our model x minus, and we are trying to push the energy of this x minus up. And this x minus can be simply generated by some sort of a stochastic optimization process where you start from some x0 and you do some gradient descent steps with some noise, and you end up with a new position x minus. And what the model basically is trying to say that anything which is not true data should be given higher energy. So once you have trained this model, at test time, you can have any input representation at x0, and you just take some gradient descent steps. And if you take enough gradient descent steps, you would end up at a low energy minima position, which would satisfy the given concept. So in this work, we built a library of such energy-based models. We have energy-based models for concepts like left, right, on, making a line, making a circle. And maybe one important thing about these energy-based models is they are composable. So we only train energy-based models for these atomic concepts like left, right, and so on. And at test time, we can just simply add up their energies, and they would move so that if we take gradient descent step on the summation of the energy of these individual concepts, we would end up with a correct configuration that satisfy all the constraints jointly. So let's look at how this pipeline works in a bit more detail. So we start with a language instruction, and we have a language parser. This can just be an LLM that maps into a program of concepts, which can be some detection concepts like the objects that are relevant for the sentence, and some goal generation concepts like the energy-based models that would be used to generate these goals. So we first call our open vocabulary object detectors, which can detect the objects that are relevant for the given sentence. Then we call our energy-based model that generates a goal configuration of where the object should be moved so that it satisfies the given constraint. And then we have some simple action policies that locally manipulate the object so that it picks up the object where it was to the goal location. So we test our model on different kinds of benchmarks like spatial relationships, left, right, and so on, circles, lines, as well as some compositional concepts where you have to move one object to satisfy multiple different constraints simultaneously, or you have to move a group of objects so that you satisfy all the constraints simultaneously. And we find that our model works better in domain compared to state-of-the-art language to action policy models like Clipboard. And it also generalizes well to these composition of concepts thanks to the compositionality of our goal generation model. We don't need to train for these compositions, it just directly works out of the box. It is robust to perceptual variations because we are using open vocabulary object detectors that really work well for different kinds of backgrounds and objects. And the energy-based models operate on this abstraction of bounding boxes that don't suffer from the background and so on generalization things. So this perceptual generalization helps in getting real robot results directly without using any real robot data. And this is because detectors generalize, the object motion graphs are working over the bounding box abstractions, which don't have any sim-to-real gap. And the local action policies also don't suffer from sim-to-real gaps, simply because they're conditioning on a very local crop. This is our result on a real-world setting where we detect objects, the EVM generates the goal configuration, and then an actual robot goes on and actually does the task. So maybe the key takeaways from this talk is similar to Animesh's talk, where you should separate what and how. Should maybe map, instead of mapping language to actions directly, you should first map language to some subgoals and then map the subgoals to the actions. This lets us generalize better and be more robust to different perceptual variations. And more importantly, each component can be trained independently, can be trained on much larger sets of data sets, and we can benefit from all the foundation models that we are building up in the community. How much time do I have? Or I'm going? Okay. So with that, I'd like to finish my talk. Thank you so much. Happy to answer any questions.
Since we're quite a bit over time, so just if you have questions, please come here, like to make questions. Otherwise, we can have a short break in